Uh, so as I start my classes, so I have to introduce myself again. Almost all of you are familiar with me right now, but still I have to do so. So I am Sripan Mandal. I am working at IIT BHU as a research scholar, PMRF research scholar, and I have to take this classes every week once for as the deliverable of the PMRF scheme. So today I am going to deliver my fourth lecture, in which I am going to solve the problems for the previous year assignment for the fourth week, which will be helpful for all of you to solve this year's assignment. So let's start with the first question. So as you can see from the lectures of the faculties, they are teaching about the ising models, and most probably they describe the ising model in 2D, but in our case we have to implement the ising model in 3D as per this assignment. So all of you are capable of seeing these questions, right?
Yes.
Okay. So the question is telling that implement ising model in 3D such that you have L into L into L cubic lattice. So you have 3 dimension, and in each dimension you will have capital L number of lattice points, and also you have to implement the periodic boundary condition and write the code such that the length of the lattice L is the input parameter of the simulation. So you can give the input of L uh, by in the command prompt, and then mode of her number of iterations at a particular temperature are also input parameters. So you have to give a particular temperature T as well as the number of iterations, and also thermal energy kBT is measured in units of J ising. So you can see this thing, or this this thing from the lectures of the faculties also. And then capital N will be the number of total lattice sites, which will be L cube, and run the simulation for the parameters given below for each question and answer the following questions. Okay, so the first question is okay. So before moving on to the first question, can anyone tell me what is the periodic boundary condition if we, let's say, if we have a single 1D lattice? Hello? 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 Someone was saying something, right? What is its mean by the periodic boundary condition?
Sorry.
Hello? Gappar?
Yeah, sir. I think L equal to we can replace by that. L equal to NA we can write as lattice constant into the number of points.
Yeah, so basically what happens, that let's say we have a one-dimensional chain of some spins, right? So let's say these are some lattice points.
0 and A we can NA.
It can be +1 or -1, right? So let's say these are my lattice points, and you have lattice points at the termination points also. So whenever you are considering the nearest neighbors for particular spin or particular lattice points, lattice sites, then for this, let's say this is I, for this it will be I plus 1, right? And this will be I minus 1, right? So for this side, these are the nearest neighbors. But when as you move to the termination points, let's say here, you will see there is just one nearest neighbor here. So periodic boundary condition tells us that for this particular case, this will be one nearest neighbor, and the other nearest neighbor will be this one, right? So this is the periodic boundary condition. Okay.
Okay.
Yeah. So likewise, if we go to the two dimension, then what will happen, that for a particular lattice site you will have four, let's say here, if we draw the two dimensional, then if this is the case, then you will see that these two will also occur, right, as the nearest neighbors along with these two. So these are the fours for two dimension. And if we have the three dimension, let's say this is the third axis, then you will see that there will be another two, right? Okay, got it? Hello?
Yeah.
So in three dimension, each lattice site will have 6 nearest neighbors, and for those 6 nearest neighbors you will basically have 3 dimensions, and along each dimension you have to incorporate the periodic boundary condition such that the termination points at each dimension or at each direction should have follow the periodic boundary conditions. And therefore you can write this code in such a manner that you will consider 6 nearest neighbors for each of the lattice sites. So let's come to the first question. So suppose all the spins in the lattice are pointing in the same direction. So the first thing what you need to do, whenever you are considering the initial condition, you have to put all the spins to be -1. Okay, and in the initial configuration, and L will be 20. What does it mean? That in each direction you will have 20 lattice sites in each direction. So that means you will have total 8000 lattice sites in the lattice. Okay, and you need to calculate the total magnetic moment. Okay, so you need to calculate total magnetic moment. So magnetic moment is actually defined as that capital M, that will be equals to summation I let's say to be the number of lattice sites is I, that means the spin at that particular lattice site. So you are just sum over all the spin components to have the magnetic moments. And if you need to calculate the magnetization, you need to just divide by the total number of spins, which will be in our case capital N, and that means L cube. Okay, so here you need not to worry about the capital N, you need to calculate this capital M. Okay, this is our motive, and here are the options given. So this questions will have some large codings, and so I am just trying to say how I can do that, or you can practice to do so. So as before, I can just have this kind of integer, real, integer, and these things. These are basically giving you the type of the variables, and then as the question suggesting that you should enter the number of lattice points and number of iterations as a input. So what this print, is it visible, right? This codes upper. Hello?
Sir, it is visible. Yeah.
Okay, so what happens is that, let's say you have, just a second, yeah, let's say you have this print star this will tell the command prompt to put the number of lattice points in each dimension, and that will be read as capital L, as well as you can enter the number of iteration, and that will be read by the code as a NITER. And what happens that you are taking up array which will be three dimensional. So here you can see that integer dimension, this line will tell that spin will be a three dimension array which will be an empty one at first sight, and then you are telling that okay, in each of the dimension you will have capital L number of elements. So it will be like a array which will have L number of elements in each direction, that means L cube number of elements in total. And then you are saying that okay, the energy at first place is 0, which is not needed to given for this particular question, but you will need to define this for other questions. Okay, capital M, which is the magnetic moment, that is also set to be 0 initially. And as the question suggests, the capital N, the total number of lattice points, that will be like L cube. And then what I am doing, that I am opening a file in which I will store the value of those kji, which are the some loop parameters. Basically they are the number of elements, or the kth element, jth element, ith element in different directions, as well as I am writing the spin kji in that particular file. Okay, so how should we do that? That for you can see in the codes given by those faculties that there will be just two loops, right? But here we are considering three dimension, so we need to have a loop in each of the dimension. And so here I am telling that okay, I, j, k, each of them will run from 1 to L, and that will cover each of the lattice sides. And for each of the lattice side, you see, for the first question you need not write you don't have any need to write this line call random number, since by question you have to set all the spins to be -1. So this line will set all of your spins to be -1 initially, and then you already initialize this lattice in this way, and you are saving all your data in this init ising dot dat. Okay, now what the question is suggesting, that you have to calculate the initial magnetization. Again we can have another thing here, that we have to incorporate the periodic boundary condition, right? So as the question was suggesting, so again I am running a loop, and here again I have to run three loops within one another, and this a b c d f g, these are basically the termination points. Okay, so what happens is, let's say whenever you are going to L, let's say if I equals to L, then what will happen? Then A will have the value of L plus 1, right? But in I direction you will have only L lattice sides, so L plus 1 will not count. So in that case A will be taken as 1. That means your first termination point will be the nearest neighbor of the last termination point. So this will be the code, or this will be the algorithm for creating the periodic boundary condition in that case. And also likewise, if you have I equals to 1, right? So for I equals to 1 you will have another set of, this will be minus, so I minus 1, that will be 0, but there will be no 0th side, right? Here is no particles or no lattice points. So what happens, that for this another nearest neighbor, that will be here, correct? So these are two things, and similarly for the other dimensions it will be given in these ways. Okay, and now I am going to calculate the initial magnetization. So initially M is given to be 0, and now you have incorporated the values of the spins in this line, and you are incorporating all the periodic boundary conditions here, and then everything is set. and you just need to calculate the summation of the all of the spins. Okay, so this will give the total magnetization. And what you have to do if you want to calculate the instantaneous magnetization per spin, sorry, this will give you the total magnetic moment, and if you just divide that by the total number of lattice points, that will give you the instantaneous magnetization. Okay, so you are going to print initial magnetization capital M is M. Okay, so this line will have the output like this. Initial magnetization in this case will come to be minus 8000, and I have taken the number of lattice points in one dimension, this L to be 20 and this number of iteration to be this number. Okay, anyone have any question? Hello, Gaffar,
Yeah, sir. No, sir.
Soumitra?
No, sir.
Okay, Dr. Said? Okay, fine. So let's move on to the next question then. Okay, so the next question is telling us that you have now, suppose all the spins in the lattice are pointing in the same direction, and in this case this is taken to be +1 instead of -1, right? Sorry guys. So these are +1s. So what we need to do is we need to initialize the lattice in such a way that we are giving all of the spins to be a value of +1, and it is asking for L to be 10. That means in each direction you will need to have 10 lattice sides. So that will give it to be 1000 lattice sides in the entire lattice, and what it need to calculate is the total energy of the entire lattice will be. So initially you are calculating the magnetization in the first place, and in this question you need to calculate the total energy, and here all the spins are given to be +1. So when I tried this program by myself, I found that this value must have some faults with it. Okay, because I was having a value of -3000 for this L equals to 10, and as soon as I took that L equals to 20, it will give you the value of -24,000, and that was the given answer in that assignment. So I think in this question this L should be taken as 20, and that will give you the correct answer. So I don't know what about this year's assignment, but I think there will be some faults in this assignment. So let's move on to the coding part and understand what I can do.
Sir,
Yeah.
so for this semester, L is equal to 10 and options are corrected.
Okay.
That means 3000 option is there.
Okay. So -3000 is there, right?
Yes, L equal to 20. You are completely right. For previous year.
Yeah. Yeah. Okay.
It must be.
Okay. Fine. Yeah. So here is the program for that. It is entirely the same as the first question. Just I have changed two things here. One is this skji, this value is 1 this time, and the second thing is here. Yeah, as before I just give all the nearest neighbors and periodic boundary condition, and here I calculate this energy like this. How? Because what I need to do is capital E. Okay, let's say the energy that is defined as minus J, right? What it will be? SI, SJ, in one dimension. Now what will you have in three dimension? It will have this kind of a thing, that minus j is, let's say you have I j k, that will give you a particular site, and the all of the nearest neighbor for this case will be multiplied with it, right? So in this case what will happen, that you need to have 1 I minus 1 ijk plus, so these are all with s, right? I minus 1 jk I am writing in this way. So the second thing will be I plus 1 jk, and then third term will be j minus 1, then j plus 1, and k minus 1 plus k plus 1. Just mind it that each one of them will have I minus 1 jk, I plus 1 jk, here it will be I, j minus 1 k, and each will have this I, sorry, this will s with all of this. So basically I am just trying to figure out how the things can be written in 3-dimension case. So here you see what I did. First I just sum over all of the nearest neighbors, okay, and I stored it to be x, and then what I did this this multiplication in this line, and then I am just adding all of this contribution to capital E, which will have a value initially to be 0, and I am taking that all the summations as the value of E, and then what I did, that E equals to E into 0.5. So what I why I am doing this, basically you have this kind of a structure, right? So what will happen is, let's say I am calculating for this one, right? So then I have to check for interaction with this particle, and I have to check for interaction with this particle also. And again, if we are going for this one, right, this one, let's say I, then I have to check again the interaction with this particle and this particle. So these type of interactions are getting calculated twice, right? For each lattice side you are calculating the individual interaction with the others twice. So what I have to do, the total energy what I am calculating by this algorithm, I have to just put a half with that, so that I can get the exact energy. So after that I can just print the total number of the entire lattice is E, and that will give you the answer of 24,000. So as Soumitra was saying that in this year assignment it is corrected. So okay, Kappar,
Yeah, sir.
yeah. So let's move on to the next question. So here for parameters, yeah, so for parameters kbt equals to, just a second, okay. For parameters kbt equals to 4.7, L equals to 10, and the number of iteration to be 50,000, the instantaneous magnetization per spin has to be calculated, and we have to show that the number of the magnetization per spin is basically fluctuating around which one of the values. Okay, so here you see you have to take the random number to initialize the lattice or initialize the spins in the lattice. Okay, so here what I have to do, I am just going to increase this, as that will be better for all of you. Okay, so what I do initially, just same way, here I changed it. that right now in this question I am calling a random number generator, and then I say that okay, so what will it give? This random number r will give me random values within 0 to 1, right? And there will be some float values that can be 0.5, sorry 0.4, it will be 0.6, 0.8, and I am looking for the values to be -1 and +1. So as I did in a previous class, that I am giving a condition that if r is less than 0.5, I can take that to be -1, and if it is r is greater than 0.5 or greater than equals to 0.5, I am going to give it to be +1. So I am just binarized those values, okay. And then as before, I am just saving those values in this data file, okay. So what else I can do? As before, I am doing the same things. I am calculating the magnetization and I am calculating the energy, okay. So in this page I just have to change this part, okay. And in the next page, what I am going to do, so the question was asking for the total energy, right? Yes, so it was asking for the total energy and how it was going to fluctuate around which one of the values. Fine. So the first one is clear, and now what I am doing is, here you see that I am opening another file, and I am this time, since my equilibrium is already since my initialization is already completed, so I am going to do the Monte Carlo steps for 50,000 times, and I have put in this niter to be 50,000, and then I am again taking 3 loops, and this time I am calling random number r 3 times, and in each time I am just basically locating my position of a spin which I am going to give a flip, and that will be in a random manner. So ijk will give you that that particular lattice size in which I am going to have a flip of the spins, and see whether that flip is associated with some minimization of the energy, or it will maximize, or it will increase the energy. And if I will see that if the energy is getting decreased, then I will take that spin flip, okay. And if it is having a increased value of energy, then I will see, or I will say that okay, so I can take that spin flip if the value of the probability of that spin flip to be greater than of a random number which I am going to generate by this constant, okay. So initially what I am doing, that as before, I am just incorporating those boundary condition, and then I am going to calculate the x as before, and then I am calculating. So here see that here I am not going to calculate the total energy, I am calculating a particular lattice size energy, okay, and that will give you the EI. And then as before, I am saying that okay, now let's say this EI is initial energy at that particular lattice site before the spin flipping, and then I am saying in this line, in this line I am giving the spin flip. If it is +1, then it will be -1, and again I am calculating this interactions with each of the neighbors, and I again calculated the energy at that particular point. So EI is initial energy EF is the final energy. Okay, then I am calculating the difference between them, which will be EF minus EI. Okay, so EF minus EI, and I am saying that okay, if DE is less than equals to 0, that means EF is less than EI, then I will take that energy or the spin flip, and I will give E to be E plus DE. What does it mean? So basically you are adding DE to E, and DE is itself a negative value, then E is going to be decreased, as well as the magnetization is calculated by this parameter. Okay, again, else if it is not less than equals to 0, that means if DE is greater than 0, then I am taking that okay, there will be a probability of accessing this microstate with the probability to be exponential minus DE by KT. So here K is taken to be 1 and T will be the temperature in the unit of the J ising. Then I am calling a random number and I am saying that okay, if H is less than U, then I am going to take the energy manipulation in account, as well as I will just calculate the total magnetic moment as before. Otherwise what I will do, I will again flip the spin, so that will give us the previous configuration back, right? So this is everything, and then what I do, I just end of all of the loops, and then I write the time, that means the number of iterations, that is going to be 50,000 at the end. So at each time it will give me the magnetization m by flow 10, and it will give me the energy per unit or per one spin. Okay, so that will write all of the values in a particular file, which is ising T47. So this one. Okay, so this is the end of my program, and let's see what is the output for this case. So whenever I am going to plot this, I use GNU plot window to plot these functions or to plot this question, and that gives me that okay, let's say you have this ising T47 N10, this one, and that what I have to do is just plot this one using 1:2. That means what you have is, in this question you see that time, magnetization and the energy per unit spin you need to calculate, and then you have to plot the time and initial magnetization. Okay, so you will have a data file which will have 3 columns, where first column is the time, that means the number of iteration, second one is the initial magnetization, and for this question you have to plot those two against each other. So in the x-axis you will see the total number of iterations, and in y-axis you will see the values for initial magnetizations. Okay, so you see all of the values are within 0.15 to minus 0.15, and except 0, the other sorry, here I think. Except 0, there will be the other values, those are quite high, right? And the that part is not going there, the fluctuation is quite low to be the other options. Okay, there is some problem, I need to fix it. So I think you guys getting it, right, how to write the programs. Gappar,
Yes.
yeah, Shomitra, yeah, Gaffar, you are telling something.
No, sir. I'm getting the things.
Yeah, I think it will be helpful, right? You have to
Yeah.
submit the assignments. Okay. So, any questions?
No, sir.
Soumitra,
Yes, sir. Yes. Yes.
so you are getting it right. I think you have already done this, right?
Yes. Yes. I have done.
Okay, fine. Dr. Said,
Yeah, yeah, fine.
okay. So I'm going to stop here today. I think the discussions will be helpful for everyone, and I'm going to upload the video in the YouTube as I do, so others will see the things when they will have some need. So thank you very much for attending the class. See you on the next Sunday.
Okay.
Okay, thank you. Bye, doctor.
Bye, sir.